Hi everyone, in this video we're going to learn how to write log functions, logarithmic functions from a table. So let's go ahead and get started. So our classic log function transformation pattern is going to basically follow this pattern. Plus or minus a log base v of x minus h plus k. A represents your vertical dilation. Sometimes that's called stretch or shrink, vertical stretch. So that is what that's going to be. And vertical dilation happens when your y values get multiplied. B is your base, and we're not changing the base at all in this lesson. There's a possibility of horizontal dilation too with a coefficient to x, but we're not going to be dealing with that today. We're just going to be dealing with the rest of these transformations. So H is going to be your horizontal translation. Your horizontal translation, sometimes that's called your horizontal shift. And then plus K on the outside of the parentheses, that is your vertical translation or your vertical shift. So you might see it called horizontal shift, horizontal translation, vertical shift, vertical translation. Okay, and the position of all of these, what were called parameters, A, B, H, and K, the position of the parameters is really important, as we'll see when we start writing these log function equations. Okay, so let's look at our first example. So for the first three, I'm going to give you the parent function that kind of reveals the base, and then we'll talk about the transformation and write that equation. So this parent function is log base 2 of x. Why do I know it's base 2? My x values are getting multiplied by 2, right? And then my asymptote is 0. That's where the function starts becoming undefined. My x-intercept is 1. So remember, the vertical asymptote at 0 and the x-intercept of 1 is your classic log parent function. And then after 1, we start doubling, right? 2, 4, 8. So log base 2 of x is our parent. And this right here now is going to be a transformation of that. We're still going to have log base 2, but one or more of these three parameters, A, H, and K, are going to be affected here. So let's look at this. So we've got 1 undefined, 2, 0, 3, 1, 5, 2, 9, 3. So the y values are not changing. They're the same as they were with the parent, but you can see the x values are changing. The x values are changing. To each x value in the parent function, I'm adding 1. How do I get from 0 to 1? I add 1. 1 to 2, 2 to 3, 4 to 5, 8 to 9. So I'm adding 1 each time. So what this is a horizontal, because we're on the x-axis, horizontal shift or translation. And I'm going right 1, positive 1, positive 1. So the way I can write that for my transformation, my equation of my transformation, g of x equals log still base 2 of x. Remember, it's minus your horizontal translation, so minus 1, and that's it for your transformation equation. Okay. So your parent was log base 2 of x, nothing done to it. This transformation equation takes all the x values and adds 1 to them. Okay, and so because of the form of the equation, we put minus 1 in the parentheses. All right, so when you see that the x values are changing, at least for purposes of this unit, we know it's going to be a horizontal shift. Okay, let's go to the second example. So our parent, we have asymptote at 0, we have an x-intercept at 1, then we start tripling. So this parent function is log base 3 of x. F of x equals log base 3 of x. Okay. Now let's look at the transformation. So we're telling you straight up, it's still going to be log base 3 of something, but what has changed? The x values look pretty much the same. The y values look different. Undefined is still undefined, right? You can't add or subtract from an undefined value. But here we go from 0 to -2. We go from 1 to -1, 2 to 0, 3 to 1. So we're taking away 2 every time. So this whole graph is the same shape, but it's going to be shifted down 2 spaces vertically. So this will be a vertical shift or vertical translation down 2. Or you could say -2, vertical shift of -2. So how do we write that given what our function pattern says? Well, the only thing that's changing is the k, vertical translation. So g of x equals still log base 3 of x. And then on the outside of the parentheses, this is important because inside is horizontal, outside is vertical. The outside of the parentheses, we can add -2, but what's a simpler way to write that? Plus -2. It's much simpler to just write -2. And then we can be settled. Okay, and that's that. Okay. So we've got a horizontal shift example, a vertical shift example. It's safe to say that we're probably going to do a vertical dilation next because that's the one we haven't done. Okay, example 3. This parent function is log base 7 of x. So for here we have f of x equals log base 7 of x. Okay, and then this is a transformation of f of x. So what's happening? My x values aren't changing. My y values are changing, but they're not shifting because 0 is still 0, but now 1 translates to 3, 2 translates to 6, 3 translates to 9. So there's going to be a multiplication operation going on here. 1 times what would be 3, 2 times what would be 6, 3 times what would be 9? 3. So here we have a vertical dilation of 3. Okay, so that means that in front of the log, we're going to put 3. Okay, so for my g of x, I'm going to write g of x equals 3 log base 7 of x. And I'm happy with that. I'm just going to circle it and leave it there. Okay, why doesn't the 0 change is a question I get asked a lot. Well, 0 times 3 is still 0, right? So dilation is going to change the shape of the graph. It's going to stretch it up and down a little bit. So that's what the 3 does. Okay, I'm going to do 2 more where we don't give you the parent function. You kind of have to figure it out from either using first differences or inspecting it. But what I will say is that if you ever have to write a log equation from a graph, you can follow the same pattern, right? You can just look for some points on the graph and compare it to the parent function and figure out your transformation that way. Okay. So let's look at a couple where you're not given the parent function. So here we have 1, 0, 9, 99, 999. For this example, you might be able to eyeball it and say, okay, well, this is 1 away from 1,000. This is 1 away from 100. This is 1 away from 10. So I'm going to say base 10. And you'd be right. It is base 10. But if you ever get stuck, a little kind of tool that you can use is what's called first differences of the x values. So your first differences would be subtracting the largest x value that you see in your table from the one right before it. So 999 minus 99 would be 900, right? 99 minus 9 would be 90. 9 minus 0 would be 9. And really you only need 1, but I just want to do it to illustrate the point. If you divide 900 by 90, what do you get? 900 divided by 90. You get 10, right? So 90 times 10 is 900. What about if you divide 90 by 9? 90 by 9, that's 10, right? So if you take the first differences between some of the x values and then divide those first differences, you'll get the base, which is 10. So like I said, for some people can just kind of see that right away by looking at it. Not everyone can. So it's just a sort of a tool for you to use if you ever need it. So if the parent function was base 10, that would mean that the original x values before the transformation would be 0, 1, 10, 100, and 1,000. So what's the shift, right? Each time we're taking away 1, right? We're going from 0 to -1, 1 to 0, 10 to 9, 100 to 99, 1,000 to 999. So what this g of x represents is a horizontal shift left 1 or -1. So we could write it, the whole function, as g of x equals log base 10, or we don't really need to write base 10 because it's a common log, but we'll fix that. We'll go back and fix that in the end, of x minus -1. Okay, and then let's clean that up. So g of x is equal to log of x plus 1, and that's it. Okay. We can follow the same pattern for this one right here, the second g of x example. We've got 2, 3, 8, 38, 218. The higher the powers go, the easier it is to see what the base is, but let's do our first differences, use our first differences strategy just, you know, to practice it. So 218 minus 38 would be 180. 38 minus 8, you know, you could do it in the calculator if you wanted to, but that's 30. 8 minus 3 would be 5. What's 180 divided by 30? It's 6. So 30 times 6 is 180. What's 30 divided by 5? 6. So 5 times 6 is 30. So the base is going to be 6, right? And if the base is 6, that means our parent function is 0 would be undefined, 1 would be 0, and then we'd have 6, and then powers of 6, 36, 216, and so forth. What's the change? We're adding 2 from the parent. So it's a horizontal shift of right 2 or positive 2. So our function will be written as g of x equals log base 6 of x minus 2. And there's nothing really to clean up, so we'll box that up as our answer. Okay. All right, I hope that helps you write equations of logarithmic functions from data. Please feel free to email me if you have any questions, and thank you so much for watching. I will see you next time.